Yes, I guess first thing is to unmute. Thank you. And then I have to join with my... Now I have to join with my iPad, which I hadn't done yet. So I think it's...
Okay, and Ron, you'll have to make his iPad a co-host.
Yeah, sorry about that.
Okay,
I think
okay.
I was trying to explain that, but without the microphone working. All right. Got it. No audio. All right. Did my iPad?
Not seeing you.
Did my iPad show up?
Yes.
Yes.
And
oh, it did.
Nope, I can't share yet.
Not yet.
Let's see.
Can you do it now?
Yep. Now you should be able to.
I think that should work. Start broadcast.
There it is.
And I guess new. All right, screen there. Everybody can see me. Everybody can hear me. No? Yes? No opinion?
Yes, we can hear
okay,
you.
good. All right. Well, thank you so much for the invitation.
Do you want me to introduce you?
Oh. No, I wouldn't have thought that was necessary. But...
Well, I at least have to start recording. So welcome everyone to this week's edition of the Western Hemisphere Colloquium on Geometry and Physics. Feel free to interrupt or type chat with questions. Today's speaker is Constantin Teleman from Berkeley, and he'll talk about Coulomb branches and something.
Drinfeld centers, I think.
Drinfeld centers and Coulomb branches.
Yeah. So thank you very much for the invitation. I mean, it's very flattering, even though I wish I was more prepared for this and had a bit more finished products to talk about. So the things I'll talk about, the finished ones are quite old and the others are very speculative. So I'll be talking about, okay, it works, about gauge theory in 3 dimensions and its boundary conditions. Boundary theories, as we say now. I've given some talk in Miami, which have a lot of overlap with this one. I apologize if you've seen that. It'd probably be only a few new words compared to that one. So it was metaphorically virtually in Miami. So this connects to something that seems very fashionable now and that very much like to understand and do. That's called 3D mirror symmetry. So I'll have to explain only the part which I do understand. I think some of it is quite old, in fact. And the point of the 3D mirror symmetry is to lift to three. Well, it may be a bit of a religious thing, so everybody worships it in private. But to the extent we can say something in public, I think it's fair to say a 3D mirror symmetry is something about 3D theories on the boundary of which you recover 2D mirror symmetry. So has 2D mirror symmetry on the boundary. And just like 2D mirror symmetry, we want to connect something holomorphic with something symplectic, but actually both things in this case are both holomorphic and symplectic. So there is a B side, there's like coherent sheaf side. And that is something that's been known for a very long time, in fact, and it's a partially constructed theory for holomorphic symplectic manifold. It's called Rosansky-Witten theory. And there's something, a symplectic analog of that, which is a bit like the Foucault category. I'm not sure if it has an agreed upon name. We could call it holomorphic Foucault theory. Or Futter theory, because that is the name of the equation, which is a 3D analog of the D-bar equation that would govern the top dimension variance. And there are now some partial results in that direction, I believe. But the part that I know a little bit about from a while ago has to do with groups. And in this case, I mean, it came up from just simply from asking a basic question, which is, what are gauge TQFTs, topologically gauged TQFTs, and there's something that we would say now have to live on the boundary of three-dimensional topological gauge theory. And that in this picture that would fit in on the right-hand side. So this would be the holomorphic side. So here, pure gauge theory, I will put on this side. And so if you take this dictionary into account, that there should be a correspondence in this way, then that leads you to believe that there is a Rosansky-Witten description of pure gauge topological gauge theory. And indeed there is, although that I think it wasn't, when it was found, wasn't clear that it was part of 3D mirror symmetry, or one could guess that. And in fact, I could call it I think I may have called it already a meta theorem a long time ago, is that pure 3D gauge theory, topological gauge theory, is a Rosansky-Witten theory of a holomorphic symplectic manifold, actually hyperkähler manifold, which is the total space of a Toda integrable system. So pure 3D topological gauge theory is equivalent to Rosansky-Witten theory for the total space of the Toda integrable system. I'll recall that in a second. And there's a version for loop groups, which connects with the finite difference Toda system, a variant of a Toda integrable system. So finite difference Toda system. And as is common in this area, it becomes literally true. The Toda integrable system is connected to cohomology. And if you just repeat this construction for K theory, you get the finite difference system or the loop group. So that's a kind of thing that comes up a lot. And one difficulty with the meta theorem, the way I first stated that, is because they were almost disjoint in definition. So on this side, this was in the original version, this is very well defined at the bottom of the theory. We know what categories with G action are, whereas Rosansky-Witten theory is defined to the extent it is towards the top. So the overlap between the two sides wasn't good enough to even have precise statements. So one challenge with the original statement, so let's say an old challenge, was to extend the right side theory, the Rosansky-Witten theory, down to points, so we could work categorically in the context of extended TQFT. So extend this guy down to points. And the model for that is something which still hasn't been constructed in full generality. It's a conjectural two-category of Kapustin, Rosansky, and Saulina associated to holomorphic symplectic manifolds. So it's called a KRS category for holomorphic symplectic manifolds. Or algebraic symplectic manifold is better. For which a Drinfeld center should be what people have been assigning to the Rosansky-Witten theory for a long time, namely the category of derived category of coherent sheaves together with an interesting braided tensor structure. Should be a braided tensor category of derived category of coherent sheaves of the space X. So maybe the manifold is called X. So with a braided structure derived from the holomorphic structure and symplectic form. Was described nicely in a paper by Kapranov quite some time ago. Braided with structure. What's this structure? Constructed from symplectic form, from holomorphic plus symplectic form. Right. So while I don't know how to construct something like this for a general algebraic symplectic manifold, hyperkähler manifold, in fact, I'm suspecting something quite as clean as the original wish was does not exist. I think I know how to do something which replicates everything you need in the case of integrable systems. So spaces which have an integrable system structure, such as the ones that appear here. So I have a model. I think I have a model, a proposal for integrable system. I won't say much about that because it's based on some very old ideas of relative field theory. So based on ideas from relative field theory. It may or may not make people happy who were looking for a clean solution along the lines proposed originally, but it does have the feature that it captures what the calculations we want to do to match with the gauge theory sign. So let me back up now and explain, because that's a good model to keep in mind, the first case, the first instance of that. So old instance of this 3D mirror symmetry. Actually, maybe before I go into that, sorry, my bad. I promised I would tell you something about what these spaces are. Maybe it's a good time to do so. So the Toda integrable systems, let's say. Just a quick refresher. There's some complexity in there. We'll need to simplify a bit and then go back to say how it works. So this space, of course, will have a long history. So names going with that are, of course, Toda, Constant, and lots of others. But I think the really clean description was given in a paper by Bezrukavnikov, Finkelberg, and Merkovich, noting that for a group G, compact Lie group G, you can associate two spaces to holomorphic symplectic manifold, one built from homology and homology, namely the equivariant homologies of the based loop group and the equivariant K-homology of the based loop group. Of course, they are algebras over the equivariant homology of a point and the equivariant cohomology of a point, and then in fact Hopf algebras over these. So they define group schemes over these bases. These are the Toda bases. So they define the groups, they turn out to be abelian. So they define, so they give a complete description of the space from many points of view that you would like. So they are abelian group schemes. And have a symplectic manifold. The symplectic form has degree 2. Very correct. Whether you call them the Toda systems for the group G or the Langlands dual group may depend on your taste. I don't think I want to get into that. There's some important feature of Langlands duality happening here, because you noticed already. For a torus, for example, for G is a torus. These are the, if you take complex coefficients, you get the functions on the cotangent bundle of the dual torus, Langlands dual torus, mapping to the functions of the cotangent fiber, one of the check. This being sim of the dual Lie algebra, which is the cohomology of BT equivariant homology of BT. So the fibers are dual tori. In general, the fibers are described in terms of the dual group. So there is a, I'll just say that because I won't use it. There is a description in terms of the Langlands dual group. Geometric description. Langlands dual group. But just to depict the basics, what we find inside, so let's just draw the integrable system structure. So you have the total space, let me call it Z for a reason I'll explain. And it projects, of course, to the Toda base. And it has a unit section and the fiber over the base point. And the case of the torus, this would be T check. This would be a copy of the Lie algebra. This would also be a copy of the Lie algebra. This is the abelian case. Non-abelian case looks a bit different, looks a bit like a blow up of this. So there's still a holomorphic. The Toda base is T mod W, which is G mod G. And there's the bulk space, Z, let's call it. Oops, I'm doing it wrong. And there is a section, the unit section again, and there is a fiber over the origin, and the fiber is a change of the homology. Actually, we're working with homology of the base loop group, and it does match the torus case if you work it out. So we have this, and they intersect at one point. And I don't want to start explaining from the beginning what the representation theory of categories work, but let me just say that categories with topological group action, if they have some nice extra property, categories with nice properties, let's say really nice properties. For example, I think I want several things. I want the Hodge-Ram sequence to collapse. I may want Calabi-Yau. I forget if I ever got rid of that condition, Calabi-Yau condition, and so on. Give rise to, can be sheafified over the Toda space. So I have a support on Lagrangian variety, and then you get a sheaf of categories on top of that. So you get a kind of thing that Kapustin, Rosansky, and Saulina wanted to describe in their category. So get to sheaves of categories with Lagrangian support on the Toda space. And if you look at the Hochschild homology of that, it's going to be just a coherent sheaf here, and that plays the role of the character that allows you to do a character calculus of such categories. So for example, let's do something already to something like this. The intersection points with this fiber play the role of the underlying category, and the intersection points with the unit play the role of the fixed point category. In this case, there isn't one. So this is the all right, that's a story. So the difficulty with the approach without the ambient sort of Kapustin, Rosansky, Saulina style structure is that any calculation you do, you have to start somewhere. You have to start either on the green line or on the orange line and sort of deform away from that to get the missing information. So that's why it was necessary to have some bigger context to be able to state a good theory. So I don't want to spend much time discussing this. It's very old stuff. What I'd like to do is explain a little bit, first of all, where it comes from in connection with, by analogy with finite groups, what the picture should look like, and then describe something interesting that I think gives us ground for more exploration when you add what physicists would say matter to the gauge theories, and you get the so-called Coulomb branches that are studied with some interest these days. So let's back up. So the primeval, I can't spell primeval. That was a mistake. There is that word. that correct? I'm not sure. Primeval 3D mirror symmetry, which is called electromagnetic duality. And that says that if you take a finite group F, then you have two tensor categories naturally associated with that, namely vector bundles over F with convolution product and representations of F with natural tensor product. Oops, that was a different color. My bad. And well-known theorem is that there's a Morita equivalence between these two. So part of the story, if you want the complete story, is that they have isomorphic Drinfeld centers. So you take the common Drinfeld center Z. And of course, that acts on either of these, so vector of F and on rep of F. So they're both algebras over Z. And they have a common bimodule, which is the one which induces the Morita equivalence. So this actually this way, say if you have a BTC, you have a tensor category, you just have a category. And one feature of this diagram is that this is compatible. One feature of a diagram is that they intersect at a single point in Z. So you would write, I guess, vector of F tensor over Z with rep F is actually vector, gives the bimodule. So you can draw a picture like this, where this is rep of your finite group. This is the category of vector bundles of a finite group. And they both sit inside the Drinfeld center. And they intersect at the point. Now, in this picture, it might be plausible that you get some kind of morphism between rep F and ZF, but it might seem surprising that this picture gives an equivalent, because after all, you only see a little neighborhood of a point at most. But of course, these are very stacky things. So this geometric extension I've drawn is fake. So the point carries all the information. That's why you get an equivalence. So point carries all the information. So the intersection gives a complete equivalence. So in the case of a Lie group, that stops being the case, and the culprit actually is not so much the group, but it's Lie algebra. So for us, we want topological representations of the group G. And while there is a range of possible definition, the simplest one is to mod out by the Lie algebra. So the categories you might want are, are vector bundles on G mod, the formal group. You could think of it as D modules on G or modules of a Durham complex or whatever, again with convolution in some form, and a rep of G mod G check with a tensor product. So one thing I'll do today, I'll remind you of a very concrete model for this, because you're probably not used to thinking of the presentation of G mod G check. And what goes wrong, or the problem, if you like, is from modding out by the Lie algebra. So you might want to think that you're, in addition to G, here you also have the group B2 of G check, G hat, sorry, the formal. It makes a lot better sense in the abelian case. So there isn't B2 of the formal group in general. Nevertheless, a lot of algebraic construction work as if there was one. So let's just point out, in fact, you get exactly the same picture in this case, but let's erase that. So the Lie algebra case, let's say it's the Lie algebra is T to make it clear it's abelian. You look at vector bundles on B of T with convolution, this tensor category, and reps of, that should be in green, shouldn't it? BT with the tensor product. And you try to interpret them, and in fact, the story works. There is some kind of equivalence after localization. So after of the categories. So if you start spelling it out, you get ST modules with tensor product, because after all, vector balance over BT are T modules, and the convolution becomes a tensor product as T modules. And well, here you may have maybe more than one interpretation. My T is illegible, sorry. But one possible interpretation is modules over lambda T in degree, shifted by degree -1 with the convolution product. Another one is, I'm not going to spell out why these are both reasonable interpretation of the same thing. But if you're worried that they look different, in fact, they're not, because these are causal dual to each other. And to some extent, it's a matter of taste which one you want to think of as an incarnation of representations of B of a vector space. But at any rate, whichever you take, there is a computation you can do in algebra, which is the E2 Hochschild cohomology, which is some localized Drinfeld center of the two tensor categories. And you get exactly the picture I drew up here. You get what you get is sim of T tensor with the sim of T star in degree 2 with a tensor product and the braided structure coming from a symplectic form. On this category, not the general braided structure. But the two sides, they came from, do correspond to the complementary Lagrangians, and they intersect at the point, but now all you get is an equivalence, a Morita equivalence of categories once you localize the point of intersection. So that's a difficulty. And the difficulty that you see in the Toda system, exactly as I was telling you, you have to commit to one Lagrangian or another before you can start doing homological algebra calculations. All right. So now let me tell you quickly, first of all, two things. So first of all, at least one incarnation of this category, representation of Gmod G check. And second, the morality claim that the Toda system is its Drinfeld center. It's an uncompletion. And I might skip over, well, I'll just say that exploiting the integrable system structure, one can execute the uncompletion and move away from the neighborhood of Lagrangian to see what's happening in the rest of the story. And then I'll go into reviewing what might be happening when you add matter. So that's a plan next. So next. So that was number 3. So 4. What is rep of Gmod G hat? And one answer is curved carton complex.
Sorry, Constantin, may I ask a question?
You may ask many, as many questions as you like.
So can you say a bit about what these categories have to do with 3D pure gauge theory?
So these categories are tensor categories, therefore they generate three-dimensional theories, and they will be describing 3D gauge theory. So they're not just categories. If they were just categories, they'd be defining 2D theory. But so
it sounds like they should be categories of line operators on a particular boundary condition. And I was wondering how Gmod G check appeared.
So, I mean, I don't think there's anything wrong. Think of them as line operators, but yes. Well, how do you actually? That in fact, it's right. I can give you an answer. So, if you think of gauge, what are line operators labeled by? For example, Wilson lines. So, be labeled by representations of the group. But the group here is just the underlying topology of the group. So you have to mod out by anything contractible. And the only contractible normal subgroup you can find in G is the formal group at the identity. So that's remodeling out by. So you from that point of view, I think that is completely correct that the labels for your Wilson lines should be representations of Gmod G hat.
Thanks.
These are the Wilson labels.
Yeah.
You'd like to impose an integrability condition on those because you really want to model by topology, not by infinitesimal topology, and that's actually one of the difficulties and one has to go around in constructing the even the KRS category rigorously. So that is correct. But if you want to write something down that's uncontroversial, I think that's what one writes down.
Yeah, I mean, I'd want those to be lines on a certain boundary condition, and then the Drinfeld center should be lines in the bulk, because that thing is braided.
That is correct. So I think that is correct. In fact, I think with that story, in fact, I don't think I want to return to that, but that's one way I know how to make the Kapustin-Rozansky-Saurina category precise, not as a standalone object, but as a theory relative to the bulk 4D theory. Mm-hmm. And the bulk 4D theory is not quite invertible. It's sort of invertible for sufficiently integrable objects. If you start computing in a place where you'd expect to get, say, the constant sheaf, you get the sheaf of D modules, which isn't quite, it's kind of Morita equivalent to the constant sheaf. You were very, very generous. So somewhere in the story, that's a good story, but somewhere in the story, one must impose an integrability condition. And one way to do so is exploiting the integrable system structure. So, and it is not entirely a pun on integrability. I mean, they do mean different things a priori, but they end up meaning the same thing. They're allowing you to move away essentially from the zero section into the bulk and detecting what's there. That's if you have this picture in mind of a relative theory and the 4D theory coming from the center, then that's in fact the good answer. And the picture suggests that's a good answer because that's where, no matter how you approach a gauge theory, that's where all things want to live. That's a one place where you can put everything that you would like to see. And that was a bit too metaphysical, sorry, but it can be made precise.
Yeah.
All right. So one answer is a curved carton complex, which is something that probably should be taught in grad school because it's almost there. It's a way to fix the problem in the carton complex that d squared is not zero. I have to take invariant before d squared is zero. So what do I remember a curved carton complex is? So it's a tensor category. It started with a category. The category is a cross product of G acting on the functions on the Lie algebra, so sim G star. And but you have to put a curving on it. The superpotential, which is psi A of the delta function at one tensor psi A over base of G. Oh dear.
Are you muted, Constantine?
Indeed, I was. All right. Can you see my screen again? Sorry, I was bumped off by some little mishap on my phone.
Yes, you're good.
All right. So a different way to write it superpotential, it's e to the w is a function from the base, if you like, G star to the group G, which is just the exponential map. And normally it's a curved category. The category of the underlying category is a category of curved modules. Normally that's not a tensor category, but it actually is because of a funny fact that we're using convolution on G and pointwise multiplication on G star, and W becomes additive in this way. So this is the tensor
Sorry,
category.
Could you also explain the line above that? Because I think you might have been muted as it was happening. So
this line,
yeah, that line.
So yeah, so I mean, this is these are the functions. It's an algebra of functions on G. The group acts on that, and you can form a cross product of functions on G with values in functions over the Lie algebra G, but using multiplication pointwise on G and convolution on the group. It's a cross product construction. Maybe I'll say it's very easy to write down the abelian case. So G is T. Spec of that, you can describe this underlying space. You break up into Fourier modes under the group, exploiting the fact that the action is trivial. So you get the union over T of sheets of the Lie algebra, and W is a map that takes the algebra element psi to the linear function lambda of psi. And the tensor structure is addition of lambda. So tensor structure is pointwise on T, pointwise on each sheet, and addition of sheets, addition of labels. If you do immediate computation, you'll find that this would make everything so the zero sheet disappear. But actually, that's one of the mistakes, if you like, one of the flaws of the usual matrix factorization calculations. So the uncompletion of the Toda system sees the whole story. So this is a tensor category I was writing. And the Drinfeld center, let's do so morally, the Drinfeld center of this tensor category is going to be, well, for a single sheet, you would get the braid tensor category coming from the cotangent bundle of that, with a grading on the fibers. You also have the group, which is now the group of co-characters acting by multiplication. And what the superpotential does here is makes that group of co-characters divide by vertical translation. No, it's not co-characters, it's a character, sorry, so lambda are the weights, not co-weights. By characters. And if you do that, you get, of course, exactly the cotangent bundle of the dual torus. So the moral statement is that the Toda space is the uncompleted Drinfeld center of the tensor category defined by the curved carton complex of the tensor category given by the CCC. So this is the tensor category. If A is an algebra or category, with Gmod G hat action, well, to describe a Gmod G hat action differential setting, you would have to write, well, first the Lie algebra of G must act on the algebra or on the category, so it maps to Hochschild 1 co-cycles of your algebra and call it the Lie action. And then you have to mod out by the, so it's degree 0, it's degree -1, you have to mod out by the Lie algebra and degree 0, that should map to 0 co-chains. And here a Hochschild co-boundary could connect that, and this should commute. And this should be a map of a DGLA morphist defined from the action of the Gmod G check on an algebra category. And to do it, actually, once you're in this world, what you really need to define are L infinity maps. So the point is that in many examples, this map need not be linear. The map on degree minus 1g. So in fact, any polynomial function, invariant polynomial function on G would give you a possibility of an action of G mod G hat on a category. So even for the category vect, you can take any function on the Lie algebra and say that defines the topological action of G on vect, and you can compute the associated gauge theory. So G mod G hat acts on vect by using the quadratic Casimir, so by the quadratic function, the quadratic form on G. And when you compute what you get from here, if you gauge it, you get topological Yang-Mills, 2D topological Yang-Mills. You begin to recover Witten's calculations of 30 or so years ago. So that's a sanity check that this makes sense. There are some other sanity check examples, some other sanity check exists. One of them is G's S1, and in that case, you can make it even more specialized. Let it act trivially on the categories. Let it act trivially, but let the trivialization of the action be interesting. Right, so that means the trivialization is here. You can map the Lie algebra, which is just the line C, into the Hochschild co-cycles, zero Hochschild co-cycles of the category in any way. So that defines a superpotential, a curving of the category. So interesting trivialization defines a curving of the category. And the fixed point computation defines a, well, what do you think the BZ, sorry, I'm sidetracking a bit and skipping a bit. So this defines, I should say, a BZ action, a BZ integral action, or an automorphism of the identity, which is e to the superpotential in the usual way of writing that. And the fixed point category, well, let me quote a theorem instead of going through some motions here. I think in this version is Trodi-Pregel. The fixed point, the Tate fixed point category is what we usually call the matrix factorization category. So let's hit trivially on A of A with superpotential W. So that would be a very special case of fixed point computation using the curved carton complex. Okay, so that's I was claiming earlier that the moral statement that the total space of a Toda system wants to be the Drinfeld center of this tensor category. So, or of rep of G mod G hat. So let's do a moral calculation. I mean, that's not justification for it. I'm going to claim that the fiber of the Drinfeld center over the base category, tensor category, is the fiber of a Toda system. And you can have fun with calculations like that, because since you're guessing in a way what the incompletion is, they're not really, you're not really forced very much to stick to any rules. But here's the cartoon calculation of the fiber. The fiber is take vect tensor vect over rep of H mod H check, H hat, sorry. So you pick, I'm skipping step, pick psi in the Lie algebra with centralizer, a subgroup H of G. And then the curved carton complex becomes equivalent to the carton complex of the centralizer in that point. And there's a quick calculation you can do, which it's exactly right for finite groups, but in this continuous case, you'd have to define things before it becomes true. And it's something like this, vect tensor rep of H with rep of H, tensor over. So I've done nothing so far. I've inserted an unnecessary term in the calculation. But now these are things you can calculate from, again, for finite groups that are exactly right. This fellow becomes rep of H hat. So that becomes vect tensor over rep of H hat. And by some version of electromagnetic duality, this becomes vector bundles on the group H mod H hat. And these are now, if you like, D modules or modules of local systems over the group H. And that is a category of those equivalent the category of modules over the fiber over the Toda integrable system. So the module category becomes equivalent to, by the monodromy representation. I feel I've gotten into too much detail already. By the monodromy rep on H to the functions on the dual group H check on H. In the abelian case, it's a dual torus H check. In the general case, a centralizer in the fiber of a Toda system. Sorry, the way I've done it, you can only see it when H is abelian, but it does work in general for dual group H check if H is a torus. Maybe that was a little too, getting a bit too much to justify that things fit together. So in any case, there wants to be here some incomplete calculation of Drinfeld centers, which produces this space with interesting geometry over the base. And the moral maybe to take away is that this innocent looking section here really carries in a lot of internal structure in order to really be the boundary condition, the gauge theory boundary condition you think of. So I don't think I want to go into how one uncompletes the calculation, partly because my method of doing so requires you to guess the space in the first place before you can justify the calculation. So it's not a good way to discover the space. What I like to illustrate is what happens when you make some changes. So this is section 4 or 5. So this was 4. So 4. What changes when we add matter? By the way, I forgot to ask, is the stopping time 50 minutes past or 1 hour past?
1 hour.
1 hour, all right. So the matter fields one must add, physicists tell us, are quaternionic representations of G. And what one is looking at then is gauge theory for G, topological, acting on something like the quantized Heisenberg algebra of E. Let's call it E. And the key example are the polarized representation of B plus B dual. So the mystery is what that is. That's meant to be associated with this mystery holomorphic Fukaya category. Fukaya 2 category. So when E is polarized, a good toy model, which actually leads to a correct answer, although I don't know how to justify the method, just to compute the answer, it's correct. A toy model is the endomorphism, the tensor category, which is the endomorphism of the Fukaya category of D. When E is not polarized, cannot be split like that. There is another way to get to the answer, which involves, interestingly, symmetry breaking and partial symmetry restoration. You can certainly break the symmetry to the maximal torus. At that point, is of course polarized. And then it turns out you can restore the Weil group. And there's a computation which shows you get the correct answer. I'll state the actual. This part is speculation, if you like it. And the speculative explanation well, how do you break symmetry to a torus? By fibering things over the flag variety. Is that you consider Gmod T or G cross over T with E and polarize that. You can certainly do that now. And that becomes then a boundary condition for the three-dimensional theory. It's a fairly complicated one because the Gmod T it's a fairly complicated boundary condition for pure gauge theory. They polarize that and form the Fukaya category, I should have said. But there's a limit as far as G of T goes when the boundary theory becomes simple. That's sort of the anti-classical limit. It's a limit when the QIs in quantum cohomology go to infinity. Gmod T theory simplifies to just sum of trivial representation labeled by the Weil group. I'm jumping some steps, quite a few steps here. So at that point, you don't see the flag variety anymore, just see somehow what's left of the polarization of P. And interestingly enough, you can descend back under the Weil group to compute something which has a good chance of being the Coulomb branch non-polarized case. So it turns out can descend back under the Weil group. So if this is correct, I mean, since I don't know an a priori definition of the Coulomb branch in general, I cannot promise that the recipe I'm about to give gives the correct one. I should point out there's a paper fairly recently by Braverman and several collaborators that give a proposal. I think Sam Raskin, maybe Misha Finkelberg are among them, Theo Johnson-Fried, and a few more. They have a proposal for the Coulomb branches. I have not yet had the chance to check if what I'm constructing matches theirs, but it matches something else that I know. So that's why I had a chance of working. So I think for the physicists, maybe the question would be, why is it that this construction has a chance of seeing everything you want to see about the Coulomb branch non-polarized case? Because it's not, I can't guess an argument of why that would be true. But the formula I'm about to give suggests that's true. So let's state the theorems. Okay, fine. Same theorems. So some are old, and I think one is new at least. So for each quaternionic representation, E of G, there is actually each. So let me put a star here because there are some tweaks, but I want to clutter the text now. There is a space C of G E mapping to the Toda base, which is it's almost a homogeneous space for the Toda system. It's not quite, so almost homogeneous. I'll make that more precise. Group scheme. And here are now some properties. So moreover, so if E is polarized, then this is birational to the Toda space. If not, it is birational to a torsor of order 2 over a Toda system, and might or might not be birational to it. I don't know if it's always the case. To a torsor. Kind of follows on the next one. There are multiplications C of GE, C of GF, let's say, to C of G, E plus F. Kind of it's multiplicative in the representation. So in particular, and these are compatible with projection to Toda base. So let's say over the Toda base. So in particular, Toda's group itself acts on all of these. The polar, well, let me say it this way. So the C of GE are homologies, equivariant homologies over omega G of a system of coefficients for homology, let's say H sub E, which is multiplicative for omega G. So it's a construction of these systems that's interesting. So in the polarized case, constructed by Braverman, Finkelberg, and Nakajima. So in the non-polarized case, there is a recent construction which seems to go by different methods. By Braverman et al., let's say. But there's also a topological tweak of the construction. Of this construction, but I don't know, I haven't checked if those agree yet. I mean, apologize for that. I was hoping to have been a bit more advanced. That construction is a bit complicated. Well, it's actually very clean and very natural in some way, but it's very complicated to see what you get. Maybe I should, that's the correct way to say that. So there is a concrete construction from Toda space and the superpotential of the gauge linear sigma model for a polar half of E. So in the non-polarized case, you have to break the symmetry before that exists. And it's as follows. So maybe I'll say, I have 2 minutes, I'll say in the polarized case, in the polarized case, what you do, you construct a subring of functions on the Toda space, so on C of G0, which remain regular under translation by a rational Lagrangian section. Vertical translation. And the section is exponentiated differential of the superpotential of the GLSM. In the non-polarized case, of course, it doesn't even exist. So what you do is pass to a Weil cover of base, choose a positive half, of E, and use the same superpotential, essentially. Use GLSM superpotential to define a rational action of the Weil group. And descend back. So take the invariant functions are not just invariant in the Weil group, but also survive this modification by vertical shift, which forces some vanishing condition. And I claim that this gives the function on the Coulomb branch of G and E. And the star, just so it's not completely wrong, there are some mode 2 obstructions in the non-polarized case that have to be removed. They show up in signs when trying to find the Weil action. So maybe I'll stop here. What else I was going to say is I was going to try to speculate about what changes one might want to make, because I think that is a question to which I don't know the answer. What changes one might want to make to this category here, to representation of Gmod G check coming from the representation, so that the Drinfeld center computation replicates what is happening here, replicates this regularity condition of surviving vertical translations by something which physicists have been writing down in the GLSM for like 30-something years almost. And I think maybe I'll stop here because I'm out of time anyway.
Okay, thank you, Constantin, for a great talk. Are there any questions?
I could try one.
Go ahead, Ron.
So you're working with the Toda system, which basically has to do with the geometry of a rational curve. In other parts of the story of 3D duality, one sees the Hitchin system coming in, or various other systems that have to do with higher genus curves. Are these two completely different stories, or do they somehow connect?
I don't know that they intersect. I mean, it's. I think when I started out thinking about this, I was hoping to see a lot of Langlands duality in, but one sees in a very mild way. There's a description of a Toda system from the center, from the what's centralizer in the dual group, but that's. I have not been able to see much more than that of Langlands duality. But initially in the Bezrukavnikov, Finkelberg, Merkovich work, I think they got into their description precisely because they wanted to track more of Langlands duality in here. So yeah, there are directions one could exploit. So for example, where are we here? I mentioned that the fiber can be identified with the homology, spec of the homology of the base loop group. Now, one knows that there's much more interesting structure on sheaves on the loop group if you use perverse sheaves, of course, and then you get close connections to the representations of the dual group. And the fact that this algebra is graded and yet we're treating it as if it wasn't degree 0 has a bit of that flavor. We really like to work with a different T structure on constructible sheaves and make more contact with the dual group, but I'm afraid I don't have anything to offer in that regard. Yes, it wants more somehow, the subject. But, yeah.
Thank you.
Other questions?
I had one. So in pure gauge theory, the Coulomb branch is smooth. Is smooth and affine.
Yeah.
And when there's matter, it's no longer smooth. And in the case with matter, I'd expect to see some significant difference between like what the field theory assigns to two manifolds, like functions on the Coulomb branch, and higher categorical objects. As in, like line operators wouldn't just be sheaves on this singular space. They're likely.
No, see, the
more
singular space doesn't seem right. The singular space is already a localization of the actual Drinfeld. I would not expect the Drinfeld center to be the category of sheaves on this with a Poisson structure. It should.
Yeah, sorry, that's what I meant.
Yeah,
yes.
No, I wouldn't expect so. I think that's sort of like a. Though that is actually the second Hochschild homology, as they call it, which is believed, which is always some localization of the Drinfeld center, but you want to actually build a braid tensor category, and this is only some forcible affinization of it. So one can try, but I don't have an evidence for that. We can try to, instead of looking at the functions to revive translation, I think of it as defining some gluing of the two copies of a Toda system, and you can try to write the same gluing on the categories and see do you define a slightly better behaved category as that limit. So
yeah, I guess I'm wondering if you can actually exactly if you can probe that singularity and get some.
I think it's a very good question, and the only thing I know about it, I've Ben Gamage and Justin Hilburn, maybe other collaborators, have been working in the abelian case, but they've been working on singular version of a Toda system and trying to build the actual tensor categories of which this would be the center. So if they got it right, then they also got the centers right. And so I think that this is fairly recent though. So I don't know much, but I second your question. Let's put it that way.
Thanks. Yeah.
Constantin, I have a side question. I somehow missed, what did you call holomorphic Fukaya category?
I didn't describe it at all, but it's meant to be a two category, actually. That's a category where the objects are being holomorphic Lagrangians, and homs between two of those are meant to be, I think, Fukaya-Seidel categories built from one of the other symplectic forms on those. So, and I believe there's recent work that makes it precisely in special cases. So maybe Rezchikov is a name that comes to mind. So the vague conjecture that way has been around for a long time, that something like this should exist. And my understanding is that there are some results in that direction now, but I certainly didn't work on that.
Mm-hmm.
But the Mofte might be able to tell you what the physicists think it is. So,
okay,
I will
maybe a further discussion.
I will ask him. All right. Okay.
But I think I told you in one case, I told you a toy model for it, maybe, or was it the case of a double of a representation? I think I'm claiming that this is not a bad model for it. The endomorphist category, the Fukaya category of half the representation. You can use this as a toy model to justify a posteriori the construction I'm giving here of two copies of the Toda system, or objects have to withstand shift. That Lagrangian is a mirror of the representation. So the objects you want in this Coulomb branch would be object in the Toda system which can withstand tensoring with V and tensoring with V dual in some sense. So there is something which looks like it's a good starting model, where this would be a good starting model for what it should be. But for a general space, I don't think I know how to do that. It's believed to be defined, I think, for hyperkähler manifold, which emit an SU2 hyperkähler rotation. I think, and then you can. It's a conjecture that I think that in top dimension, the moduli space you get by counting solutions of Futter equations give you well-defined topological answers. I don't know of any theorem approaching that. But
yeah, but morally it should correspond the level of cohomology of this cohomology with coefficients in the sheaf of vanishing cycles, so that potential which you just mentioned.
Something, yes. I mean, so I think, and if I remember correctly, the first attempted construction of the Coulomb branch by Nakajima were exactly pursuing that direction. That's correct. Yes.
But it's not done. Yeah.
Well, I may not be the person to ask. I don't know the latest. I would say maybe 2 years ago when I last looked, there wasn't a candidate definition in general. But things have moved since then.
Okay. All right. Thank you.
Any other questions?
This is a request, not a question. If you could save that document you've been writing on as a PDF file and send it to me, we would love to post it on the website next to the video.
It's pretty unreadable, but yes, I can do that.
All right. Well, with that, let's thank Constantin again for a very stimulating talk.
Thank you for inviting me again, and I hope I didn't waste your time.
Not at all.
All right.
Thank you.
Thank you.